Hi, I'm Güvenç, and this is my video explanation for task 8.1p. I will go through each part and explain my approach and walk through the circuits. For part A, Miss Marple wants to find the hotel with the most shortest path from the train station. Since all edges have weight 1, this is an unweighted graph, so BFS is the right tool here. It naturally finds the shortest distance because it explores nodes level by level. But I don't just need to I don't just need to shortest distance. I also need to count how many shortest paths exist. So I modified BFS by adding a second array called count and alongside the usual dist array. Now let me go through my sucode. For this, the first block initializes everything. The dist of s is set to 0 and count of s to 1 because there is one trivial path from the station to itself. All other nodes start with distance infinite and count 0. Then the main BFS loop starts, and I decree a node U and look at all its neighbors V. There are three cases here. The first line, uh, if V hasn't been visited yet, meaning dist of V is still infinity, then I'm discovering it for the first time, and I also set the dist of V to dist of U plus 1, and I copy the count from U to V. That makes sense because the every shortest path that reaches can be extended by this 1H to reach V. And second line, uh, if V was already visited and dist of V equals dist of U plus 1, that means I found another way to reach V at the same shortest distance, just coming from a different node. So I add count of U to count of V. This is how multiple shortest paths get accumulated. And the third one, the if the another condition is the tree, uh, path go through U is longer, so I skip it. And there is no explicit line for this. BFS just moves on. And at the end, uh, the hotel with the highest count value is the one Miss Marple should pick, and the whole things runs in O n plus m because it's just a BFS with one extra operation per h. And for the part B, I need to test it, test if a communication network is connected, meaning every computer can reach every other computer. And the idea is simple. I pick any node, say uh, node 0, and run BFS from it. Now let's look at my code. And for at my code, as the BFFs runs, I keep counter called visit count, and the every time I discover new model, new node, I increment it. So after the BFS finish, I check the if visited const equals n. That means every node was reached, so the graph is connected, and I return true. If visited count is less than n, some nodes were never reached. They must be in a separate component, so I return false. And the reason BFS uh, is enough is that BFS visit everything reachable from the starting node. In a connected graph, that's all n nodes. And if it's not connected, at least one node won't be reached. So that's also, as a time complexity, runtime is O n plus m, and one pass through all nodes and edges. For the part C, first of all, ask us what happens to DFS runtime if we switch from adjacency list to an matrix. With adjacency list, when DFS visits a node, it only loops through that node's actual neighbors. So across all nodes, the total work is proportional and to the number of edges, that's OM plus M. And with adjacency matrix, for each node I visit, I have to scan entire row to find which entires are non-zero. That means checking all n columns, and even if the node only has two neighbors, I still check all n columns to figure that out. So n nodes times n columns per node gives a n squared. This is worse than on plus m, especially for sparse graphs where m is much smaller than n squared, and the matrix wastes time checking entires that don't represent actual ages. If we move on to part D, I extracted the edges from the 10 by 10 cos adjacency matrix and run the Dijkstra's algorithm from node 1, and let me walk through the first 5 steps in detail. And I initialize this at the step 1, I initialize the dist of node 1 to 0 and everything else to infinity. The priority queue starts with just 0 to 1, and I extract node 1, and it's the only one in the queue, and node 1 has two outgoing edges, uh, to node 2 with the weight 4 and to node 6 with weight 10. So I update this of node 2 to 0 plus 4 equals 4, and this of node 6 to 0 plus 10 equals to 10, and both nodes enter the queue. The priority queue is now the 4 to 2 and 10 to 6. At the step 2, I extract the node with the smallest distance, which is node 2 with distance 4, and node 2 has 4 outgoing edges, to node 4 with weight 5. So 4 plus 5 equals 9, and that's a new discovery. This of node 4 becomes 9, and uh, to node 5 with weight 11, 4 plus 11 equals 15, and this of node 5 becomes 15, and also to node 7 with weight 8, and 4 plus 8 equals 12, so this of node 7 becomes 12, and the node 8 with weight 10, uh, also 4 plus 10 equals 14. This node 8 becomes 14, and all four are the first time discoveries, so they all enter the queue. And at the step 3, uh, I extract node 4 with distance 9, and node 4 has 3 outgoing edges. First node 1 with weight 6, and 9 plus 6 is 15, but node 1 already has distance 0, so no update. And then node 3 with weight 2, 9 plus 2 is 11, and node 3 hasn't been reached yet, so dist of node 3 becomes 11, and it enters the queue. And lastly, to node 6 with weight 2, 9 plus 2 is 11, but node 6 already has distance 10 from step 1, and 11 is greater than 10, so no improvement. And the queue has now 10 to 6, 11 to 3, 12 to 7, 14 to 8, and 15 to 5. And at step 4, I extract node 6 with distance 10. Node 6 has just one outgoing edge, to node 4 with weight 3, that gives 10 plus 3 equals 13, but node 4 already has distance 9 and 13 is the bigger, so no update. Nothing changed in this step. The queue becomes like this. And at the step 5, I extract the node uh, I extract the node 3 distance with 11, and node 3 has one outgoing edge, and to node 5 with weight 9, that's 11 plus 9 equals 20, but node 5 already has distance 15 from step 2 and 20 is bigger, so again no update. And the remaining steps 6 through the 9 follow the same pattern. The final extraction order from the priority query is 1 to 10, and node 9 is never reached uh, because no reachable node has been H going into it, and it only has an outgoing H to node 8. The final distance and the shortest path three are the three in my report. And for the uh, part E, and let me check the part E. E asks if P is a shortest path from S to T, and we increase every H weight by 1. So the and also the we after H weight by 1, does P stay the shortest? And this is the question, and the answer is no. And I will show my I will show why with a counter example. And I have a graph with 4 nodes. SABT, there are S to A and A to B and B to T, all with weight 1, and there is a direct H S to T with weight 4, and before the increase, the pet SABT costs 1 plus 1 plus 1 equals 3. The direct pet S to T costs 4, so SABT is the shortest pet. Now, after the adding 1 to every age, SABT has 3 ages, so it goes up by 3. The new cost is 6, but S to T has only 1 age, so it goes by the just 1, and the new cost is 5. Now S to T is shorter than SABT, and the reason this happens is that the increase isn't fair across the pets, and a pet with key ages gets increase of key, not a fixed amount. So pets with more ages get penalized more, so that's why the shortest pet can change. And at part F, for part F, I'm given a graph with exactly one negative weight cycle. I know which vertices are on it, and I need to check if there is a path from S to T with negative total weight. And the key observation is this: the observation is this: the only way to get a negative total weight is to use that negative cycle. And if I can get from my from S to cycle, I can enter it and loop around it as many times I want, and each loop reduces the total cost by absolute value of the cycle's weight. After enough loops, the total becomes negative. Then I continue from the cycle to T. So whole problem reduced to two reachability questions, and can S reach the cycle, and can the cycle reach it? So I will walk through my SU code now to explain it. So at my SU code At step one runs BFS. Uh, at the step one, uh, runs BFS from S on the original graph. Then I look through the cycle vertices, and if any of them get visited, S can reach the cycle. If none were visited, I return false right away. At the step two, uh, uh, step two, my function checks the other direction, and I build the reverse graph and runs BFS from T on it, and again loop through the cycle vertex, and if any cycle vertex is reachable from T in the reverse graph, that means in the original graph there is a path from the cycle to T. And finally, if the uh, both checks passed, I return true. Negative weight path exists. If the second check also failed, the cycle can't be used. So I return false, and the runtime is on plus m, and step one is one BFS building the reverse graph is on plus m, and the step two is another BFS. That's it. So that covers all six parts, the code and the logic for each one, and the first five steps of in the detail. And thank you for the listening me.